Hey there, STEM Chemistry. This is Ms. Ruark. This is Vodcast 1.6, and we're going to talk about the trends of the periodic table. Sorry. Okay, so we're going to get into more on how to use a periodic table as a big old cheat sheet by their trends. Okay, let's look at nuclear charge first. Nuclear charge has the symbol Z. Okay, nuclear charge, the nucleus we know is made up of protons and neutrons. Oh, that's not showing up very well. Let's change that to another color. There we go. All right, so the nucleus is made up of protons and neutrons, and the positive charge of the nucleus comes from the protons that are inside. Well, guess what happens? The more protons you have, the more the charge, or the stronger the charge. Okay. Um, and yeah, so neutron wants to pay tab button. Says for you, no charge. Why? Because neutrons have no charge. Okay, electrostatic force. So electrostatic force is pretty much the same thing as the Coulombic attraction, and it deals with Coulomb's law. And when you get into AP chemistry, you will do some work with Coulomb's law. This is the equation that deals with Coulomb's law, and it talks about the electrostatic force, or the Coulombic attraction. K is a constant. Q would be the charge of one particle, Q is the charge of the other particle, and R would be the radius. All right, so what does this mean? Well, this describes the force of attraction that happens between oppositely charged particles. And we talked about this when we did the Coulombic law. Pogel, we said that if we increase the distance between those particles, that the force of attraction, or the Coulombic attraction, decreases. And we also said if we decrease the distance, that the Coulombic attraction will increase. Yes, I told you it would come back, and here it is. All right. We also talked about no, we didn't. This is new. Electronegativity. Electronegativity talks about how tightly the valence electrons are held in, or actually, I like to think of it in terms of which ones are greedier, which elements are greedier. Okay, so when we do a bond, or when we make a bond, or we do a chemical reaction in chemistry, everything that's happening there is happening because of the electrons. And not just any electrons, the valence electrons, right? The outermost electrons, the electrons that are in the outermost energy level. Those are the electrons that are going to form bonds. Those are the electrons that are going to make a reaction happen. Okay, so the more electronegativity, or pull on electrons, that an element has, they're going to be held closer. Sorry. So the more electronegativity an element has, it pulls the electrons closer to it. All right, now electronegativity is not something that you can go out and determine. It's based off of a calculation, and there are set values for it. It goes from 0 to 4, 4 being the highest and most electronegative, and 0 being the least. Now, not one single element on the periodic table has an electronegativity value of 0, so we would say that the least is 0.7. All right, now here is a nice little visual that shows you the lowest electronegativity is going to be over here in the left-hand corner in the bottom, and that would be with francium. All right, francium and cesium, or cesium, however you want to say it. Those are going to be the least radio or electronegative, and they both have a value of 0.7. And then as you move up, the value increases. As you go across, the value increases. Sorry. That sounds important. They better get there. Okay. All right. And then the most electronegative value would be fluorine, and that has a value of 4.0. So it is the most electronegative element, and then these two here are the least. Now, I said nobody on the periodic table has a value of 0. I kind of lied, right? Because you have these here. These are the noble gases, and noble gases don't have an electronegativity value because they don't share electrons. Okay. Oh, I left that out, didn't I? Okay, so it's the pull on shared electrons. Oh, sorry, I left that out. I'm a horrible teacher. Okay, so pull on shared electrons. So not all electrons transfer. Some of them are shared between two or more two elements, and so the ones that are shared are going to be pulled. And fluorine Well, it likes to share, but it doesn't like to share a lot. So it'll share somebody else's electron, but it holds it close. So fluorine's that one person that walks around and they're like, I need a calculator. I didn't bring my calculator to school today. And they find that one person. They're like, hey, can we share your calculator? And the person that they're looking at says, sure. And so fluorine will sit down next to that person and take that person's calculator and put it on their desk. So fluorine grabs the calculator and puts it on fluorine's desk. And the person's like, hey, that was my calculator. I thought we were sharing. And fluorine's like, yeah, we are. You just let me know if you need to borrow it. Yeah, not cool, right? Not cool, bro. Okay, well, that's fluorine. Well, guess who he's picking on? He's picking on these guys right here in group 1 because they have the least electronegativity, and they're going to be sharing. Okay? The values, here are the values here. You would look them up in a table. I'm not going to make you calculate them. When you get to AP Chemistry, they might make you, but I seriously doubt it. All right. Oh, calculated values. There we go. I added it on there. Okay. The next one we talk about is atomic radius. And atomic radius talks about the size of the atom, or how big the radius of the atom is. All right. So if it has... I'm going to be honest, I don't even know what I had going on in there. Less blank blank, smaller atoms. Takes up less space. Less... give me a second. Okay, I got it. Less energy level equals a smaller atom, which means it takes up less space. So if you'll notice at the top of the periodic table, the atoms are smaller and they get bigger as they go down. Why? Because you're increasing the energy level. All right? Yes. Okay, but they get smaller as we go across this way. Why in the world could that be? Well, do you guys remember how we talked? This right here is all about increase the distance, decrease the Coulombic attraction. Right? As we go across, what's happening? We're increasing the number of protons. So we're increasing the number of protons. What did we say happens when we increase the number of protons? We increase the force. If we increase the force, what happens to the distance? The distance gets smaller. Oh my gosh, look, it's all related. So it gets smaller because there's that pull from the nucleus that's pulling those electrons in closer. All right, so the trend, as you go down, it gets bigger. As you go across, it gets smaller. All right. On the next one, we have ionization energy. What is ionization energy? It's the energy needed to remove an electron. Okay, so energy needed to remove an electron. You can have first ionization energy, second ionization energy, third ionization energy, depending on how many electrons you have to remove, right? Okay, as you remove one electron, the first one's going to require energy. The second one usually requires more energy. The third one is going to be near impossible, or it's going to require a super amount of energy. Okay, the higher the ionization energy, the harder it is to remove that electron or a electron. Okay, cations. Cations are ones that form positive ions. Are they going to give away their electrons, or are they going to hold on to them? Well, they're going to give them, right? So it's going to have a low ionization energy because they already want to give them away, right? You don't have to put a lot of energy into something to get something from someone if they're giving it away. You just walk by, you're like, thanks, dude. All right, what about anions? Well, anions, they're going to form negative ions, and that means they don't like to give things away. They like to take things. And people who like to take things, you have to put a lot of energy into them to get things from them. And so they're going to have a high ionization energy. And look, it says ionization energy increases as you go from metals to nonmetals. It's going to increase. What do you think about going down the periodic table? What do you think is going to happen there? As you go down the periodic table, the size of the atom gets bigger. As the size of the atom gets bigger, increase the distance, what happens to the force, the Coulombic attraction on those outside electrons? It gets weaker. So do you think as they go down, as we get to the bottom of the periodic table with that weak force on those outside electrons, do you think it's going to be easy or hard to take that electron? If you said it's easy, you're correct. So as you go down, the ionization energy is actually going to decrease or get less. And why? Because there's a weaker Coulombic attraction. We call that shielding. Okay, the inside electrons are shielding those outside electrons and keeping it from, it's keeping the nucleus from holding those those electrons in. All right, and I think this one's yeah, shielding, all about shielding. Okay, so back to Coulomb's law. The distance from the nucleus is going to do what to the attractive force on the valence electrons? Is going to weaken it or make it decrease. Okay, the inside electrons are going to get in the way. All right, so here's your nucleus. Here's your outside electrons. They're further from the nucleus. Here's your inside electrons. They're getting pulled on by the nucleus, right? Guess what? So are these electrons. They're getting pulled on as well. But what happens here is they can't come in any further because there's a repulsion between these two. They don't like each other. They don't want to be around each other. They're like, get away, get out of my space. You know, they're like the two kids in the back of the car. Mommy's on my side. Yeah, that's what's happening here, okay? And since they repel each other, that repulsion right there is actually going to push it further away and it weakens that attraction there. So they shield and repulse. Yeah, I know repulse sounds so bad, right? And they repulse those valence electrons. All right. Which has more influence, nuclear charge or shielding? Well, we figured that out in the vodcast. We said that if you increase the nuclear charge, but there's more shielding and more electrons in the way, that the shielding is going to have more influence, right? So as you increase the distance away from the nucleus, you're also increasing the number of protons, but that force, oops, that was supposed to be an up arrow. As you increase the distance from the nucleus, you're also increasing the number of protons, but the distance wins over, and so the force actually goes down. So the one that takes precedence is the shielding. The shielding is the one that wins. Okay. All right, and then this just kind of breaks down your trends that I just covered with you. Atomic radius is going to decrease as you go down, and it's going to increase as you go from right to left. Okay, electronegativity increases going from left to right, and it increases going from bottom to top. Ionization energy does the exact same thing as electronegativity. And then we have metallic character, which means, does it act like a metal, right? Well, we know that the periodic table is separated by this beautiful staircase line right here, and your metals are on the left side, and the metallic character increases as you get further from the staircase, and your nonmetals are on the right side, and their character increases as you get further from the staircase. One more thing that's not on here is something that I want to talk about, which is reactivity. Reactivity. Okay, reactivity, as you get closer to the staircase, the reactivity gets, it's less and less reactive. Okay, so the further you get from the staircase, further from staircase, more, oh no, more reactive the element is. Right, and then there's one other thing called ionic radius. I don't think I put this in here either. An ionic radius is just the size of the ion, and we'll talk more about that in class, but it's going to follow the same trend that atomic radius follows. Okay, I think that's it. Yay! Okay, there you go. I'll see you in class.